Dear students, I start with lecture 31 of 202. Just check the note. We have already discussed the 1 and 2, and also there is nothing about 3, and we go further in the notes. But this is very important for further study of this paper. The set LUV of all linear transformations from U to V is a vector space under the usual addition and scalar multiplication of functions. Script M cross N set of all real matrices M cross N. Tau is function from LUV to M cross N defined by tau of P is P of P1 P2, means this is a matrix associated with P. This is 1 1 and onto and linear map, that is isomorphism. If I say this U as Rn and this V as Rm, then P given V2 we call it natural matrix. And see here something more. In the 4, there are two matrices of M cross N type, and we add them, each of them with their entries, means the first row, first column in the first row, first column, second in the second, and row and column wise. And then check the fifth one. One theorem on the board: the dimension of the vector space script M cross N is Mn. So, if you think the definition of dimension, it is in our mind that the dimension is the number of elements in the basis of the given vector space. Means we have to deal with the basis of the M cross N. So let's start. Proof. Let us define matrix Eij as ijth entry is 1 and all other entries equal to 0. How we define this? We define this for your understanding. E11, if I say E11, means this is 1 and all other entries are 0. If I say let us define E11, say instance 11, then 11 entry is 1 and all other entries equal to 0. If I define E12, first row, second column, then this is 1 and all other entries equal to 0. If I say E13, first row, third column, this is 1 and all other entries equal to 0. So definition is very obvious. Let B equal to E11, E12, E1n, E21, E22, E2n, EM1, EM2, EMN. We just define it like this. So, we claim B is the basis of script set M cross N. Means we have to prove two things. B is linearly independent, and second, the span of B is M cross N. Therefore, alpha 11, E11 up to alpha 1n, E1n, alpha 21, E21, alpha 21, alpha 2n, E2n, alpha M1, EM1 up to alpha Mn, EMn equal to 0 bar N cross N. So obviously this is the null vector of N cross N. And you know that E11 means only first entry 0, 1, all other 0, likewise all. And this shows that by the definition, therefore, all alpha ij equal to 0 for all 1 less than or equal to I less than or equal to M, 1 less than or equal to J, less than or equal to m, and therefore B is linearly independent. Just check it once for a few minutes. Also, the subset of m cross L. This implies span of B, because this is vector space. Script m cross n is a vector space. So any set of it and linear combination of that cell will be covered by the vector space. So now we choose one element in this and we will show that it belongs to the span of B. Let A equal to alpha ij, which is belongs to script m cross n. Therefore, A equal to sigma alpha ij Eij over all I and j. This is belongs to span of B, and this is true for all A in script m cross n. And this shows that m cross n is subset of span of B. We say this is equation number 2. In the equation 1, span is subset of that. In the equation 2, that is totally reversed. And therefore, m cross n equal to span of B. We have B is Li and span of B is equal to this, and therefore B is a basis of script m cross n. And so obviously, what is dimension? Dimension m cross n means numbers of elements in B, that is mn, and that we wanted. And that is the end of this proof. So check it. There is one corollary on the board. If U and V are finite dimensional vector spaces, then dimension of LUV is dimension of U into dimension of V. Proof. Since 2 from LUV to script n cross n is 1 onto and linear. That is isomorphism. So numbers of elements in LUV and n cross n are the same, as if U and V are finite dimensional. Therefore, dimension of LUV is equal to dimension of script n cross n, and by the previous theorem we know that is Mn. But this is dimension of U into dimension of V. So very simple proof is there, but it is proved now. One definition on the board, check it. Definition of range, kernel, rank and nullity of a matrix A. The range, kernel, rank and nullity of a matrix A are defined as the range, kernel, rank and nullity of the linear transformation A. That means that the linear transformation which is associated with matrix A. It is not written that, but it means that. There is a one sum on the board. Matrix A equal to 3 2 1 0, 1 minus 1 1 1 and 2 0 1 2. We have to verify rank nullity theorem. Range of A. Therefore, range of A, that is 3 2 1 0, 1 minus 1 1 1, 2 0 1 2. We have to verify that it is linearly independent or dependent. If they are alike, the range this is range of it, and range is 3. Let's check. Therefore, 3 2 1 0 1 Therefore, 3 alpha plus beta 2 gamma 0. Coordinate, first coordinate 2 alpha minus beta, third coordinate alpha plus beta plus gamma 0, third coordinate beta plus 2 gamma 0. We say equation 1, 2, 3 and 4. Now if we put this value here, one and 4 implies beta plus 2 gamma 0 means 3 alpha 0 means alpha 0. If we put alpha 0, we have beta 0. Now if alpha and beta both are 0, or by equation 4 gamma 0, therefore alpha, beta and gamma all are 0. Therefore this is range. Therefore range of A is 3, 2, 1, 0, 1 minus 1, 1, 1, 2, 0, 1, 2. And therefore, range of A, that is RA, is 3. I will discuss null space and nullity in the next lecture. I stop this lecture here. Thank you very much.